Okay, dear students, welcome to my YouTube channel. Today we will discuss the new type of material, magnetic material, that is the antiferromagnetic material. So you have to calculate the parameter, that is chi magnetic susceptibility, for this antiferromagnetic material also. Before going to this type of material basically shows different kind of behavior in chi versus T plot. Here, if you see, the behavior is like this. It is temperature along x-axis, and this is the susceptibility along y-axis. So this shows the behavior like this. So here the magnetization increases first up to a certain maximum value at certain temperature. That is called as Tn. That is called as nail temperature. So this is the different kind of behavior, because if we increase the temperature for in case of ferromagnetic materials, so there is decrease of magnetism. Here the susceptibility increases with increase of temperature up to a certain limit, and after that the magnetic susceptibility decreases after crossing this temperature range. So we can write the susceptibility for in this case will be equal to C upon T plus Tn. So in case of ferromagnetic, if you remember, this was equal to C upon T plus Tc. Tc was Curie temperature there. So the plot of this was like this. It is temperature here, it is chi. So at certain temperature Tn, Tc. So at Curie temperature, if T will be equal to, here it is minus, if T equal to Tc, so chi tends to infinite. So at Tc, chi will be infinite. So here in this case, if T equal to Tn, so chi will be finite. So this type of magnetic property of a material can be explained as if a crystal, this type of behavior was first seen in case of manganese oxide. This type of material shows this behavior first. So if a crystal exhibits antiferromagnetism, so it is considered as it consists of interpenetration of two sublattices, that is lattice A and lattice B. These two lattices are actually interpenetrating to each other. In one sublattice, there are magnetic moments in one direction, and in the second sublattice, the magnetic moments are in opposite direction. So on the basis of this explanation, we can explain this behavior completely. We can draw here it diagrammatically. If this is sublattice 1, this is the crystal lattice. Here the atoms are at their lattice situs. So the second sublattice will be like this. So in this case, in first lattice, the magnetic moments are in upward direction. This is the net magnetic moments of their respective atoms. So in this case, here the atoms are darker so that this will become visible. So at these pointers, the net magnetic moments are in downward direction here. So at the at the regions of nearest neighbors, here it is swooping up, here it is swooping down, here it is swooping up, it is swooping down, it is swooping up, and it is swooping down. So due to this interpenetration of these two sublattices, so the magnetic moments will be in opposite direction to each other. So the net magnetization in this case will be equal to 0 if in absence of any external magnetic field at 0 Kelvin. So if there is an increase of temperature, so this increase of temperature, these magnetic moments will be randomly oriented so that there some magnetization arises there. This magnetization increases if you increase the temperature of the system, and it reaches to a maximum value at Tn, that is called as nail temperature. Therefore, after that, the magnetization decreases if we cross this temperature limit. So it exhibits like a paramagnetic. So therefore, paramagnetic behavior at T greater than Tn. So before going to explain these things, we can calculate the magnetic susceptibility chi for this antiferromagnetic materials. That is, we have to derive chi, that will be equal to C upon T plus Tn. This relation. So therefore we can write, for doing this, we can take only the effect of nearest neighbors only, and the effect of others will be small and can be neglected. So therefore we can write, so due to this presence of magnetic moments within the material, they are in one direction in one lattice and opposite direction in other sublattice. Therefore we can write, so there exists a molecular field, internal magnetic field, due to the presence of these magnetic moments. Therefore we can write, if HA is the internal field due to A lattice, we can write it as H minus lambda times MB. Here lambda is the molecular field coefficient. because the magnetic field intensity at A will be equal to net magnetic field minus lambda times magnetic field, which can be cancelled by the nearest neighbor. So it will be H minus lambda times MB. Similarly, for B, this can be written as H minus lambda times MA. Therefore, the magnetization due to A can be written as MA will be equal to, we are familiar with this, N mu B into B, that will be written as mu naught H, that is HA upon KBT. Similarly, MB will be equal to N mu B mu naught HB upon KBT. This will be equal to N mu B mu naught upon KBT. In place of HA, we can write H minus lambda times MB. Here we can write also N mu B mu naught upon KBT, H minus lambda times MA. So the net magnetization due to the lattice will be the sum of these two magnetizations. We can write M will be equal to MA plus MB. So N mu B mu naught, here it is square, mu B square mu naught upon KBT will be common, and there remains twice H minus lambda times MA plus MB, that will be equal to M also, that is lambda M. Therefore, M will be equal to N mu B square mu naught upon KBT. If 2H is common, there remains 1 minus lambda M upon twice H. Therefore, we can write it as N mu B square mu naught into twice H upon KBT. Here this can be written in denominator as 1 plus. Because if we use binomial theorem, we can get back this equation. Therefore, we can write this equation as M N mu B square mu naught twice H upon KBT. Here it is 1 plus lambda M is equal to N mu B square mu naught H upon twice H. H and H goes. Upon KBT also. Therefore, M will be equal to twice N mu B square mu naught H. This twice is here upon KB. So T will be given inside, that is T plus lambda times M mu B square, because T and T will cancel, mu naught upon twice KB. So M will be equal to, this is equal to a single constant, that is called as Curie constant. So it is 2 times that of Curie constant. So we can write twice C upon T plus, so this is all equal to Néel temperature. So these are dimensions of temperature and can be written as Tn, that is the Néel temperature. So this is magnetization. Here in place of H we can divide it here, that will be equal to susceptibility. So we can write here susceptibility. So magnetic susceptibility in case of antiferromagnetic materials will be equal to twice C divided by T plus Tn. So we can calculate the Néel temperature as if the external magnetic field is 0. So H will be equal to 0, that is the external magnetic field. So we can write the equations as HA will be equal to, that is H minus this, that is minus lambda times MB. Similarly, HB will be equal to minus lambda times MA. H is here, H will be 0. So we can write this HA plus lambda times MB will be equal to 0. Similarly, here HB plus lambda times MA will be equal to 0. So HA will be HA in terms of MA can be written as, because if we can take the sky will be equal to twice C upon T plus Tn. At Néel temperature, if T equal to Tn, we can write here this will be equal to twice C twice T, that will be equal to C upon T n. The sky will be equal to M upon H. So in place of HA, we can write it as a HA will be equal to Tn upon C into MA, this equation. So we can substitute here. We can write this HA, that is MA multiplied by Tn and divided by C. We can multiply here it, that is plus C lambda upon Tn. MB will be equal to 0. Similarly, in terms of HB, we can write MB plus C lambda upon Tn. MA will be equal to 0. So from these two equations, if we write here, if T is greater than Tn, or T greater than Tn, so there is no spontaneous magnetization. Therefore, Ma magnetization due to A lattice, that is the spontaneous magnetization, will be equal to spontaneous magnetization due to B lattice will be equal to 0. So for obtaining the non-zero solution for this equation, we can write at T equal to Tn condition, so that there is net magnetization seen, and here we can write Ma, the coefficient of Ma and Mb will be equal to 1, that is C lambda upon Tn will be equal to 1. Therefore, C lambda Tn will be equal to C times lambda. So this is the near temperature and will be equal to and is analogous to the Curie temperature, that is Tc in ferromagnetic case, but here experimentally it was found that Tn is small, less than as compared to Tc. So this condition can be explained as here. So there is a condition whether the magnetic field, applied magnetic field, in which direction it can be applied. So that it can be applied by two conditions. We can take two conditions, that is if the applied field is perpendicular to the magnetic moments. Therefore, if one lattice has something like this and another lattice has something like this, so the magnetic field will be perpendicular. Both are these magnetic moments, so it can be applied either as perpendicular direction. So in this case, we can write here, if this is magnetization due to Ma and this is magnetization due to Mb, here this is the magnetic field intensity. External magnetic field will be perpendicular to this plane in which these two magnetic moments lie. So the angle between these two magnetic moments will be twice phi, because this is phi and this will be phi, that is the 2 phi will be angle between these two. Therefore we can multiply the magnetization, that is for example Ma multiplied by twice phi. So this is the magnetization of Ma in the direction of Mb. So we can write it as, and here it is molecular field coefficient, that is the lambda. So M will be also equal to Ma plus Mb multiplied by pi, can be written as Ma plus Mb. If Ma is equal to Mb, we can write it twice M phi. Magnetization due to net magnetization due to Ma and Mb. So therefore this will be equal to M actually here. This is M. Therefore we can write susceptibility chi will be equal to M upon H. So therefore this will be twice M into phi divided by, here M equal to Ma, we can write twice pi into Ma. that is m, and multiplied by lambda. So this thing and this thing will cancel. There remains only 1 upon lambda. So the magnetic susceptibility in case of perpendicular direction will be equal to 1 divided by lambda, that is constant. So if we plot this like here, this is temperature, here this is sky, therefore there is a constant value. If this is a near temperature Tn here, so the magnetic susceptibility up to Tn condition, it will be constant, that is 1 divided by lambda. So it is independent of temperature here. Therefore, if the magnetic field is applied in the parallel direction, if the P is in parallel direction, that means if this is the this, so magnetic field will be applied here in this direction. This is B. So in this case, before applying the magnetic field, this can be explained as, before applying the magnetic field, if this magnetic field is small, so it can, this magnetic moment is in this direction, so there is the one more, and it is the magnetic moment due to another lattice will be in opposite direction. So for small field, very small field, it cannot disturb this one, so it remains there. So there is one supin up and magnetic moment up and magnetic moment down, so the net magnetization will be 0. That means it starts from here. If the value of magnetic field increases, this supin will be tends to move themselves in the direction of magnetic field. So the magnetization increases as the magnetic field increases. So it starts from 0 and reaches up to a certain value. So this behavior, most of the materials shows this behavior and some materials shows this behavior. So in average we can write it as, so this is sky parallel, this is sky perpendicular. So the average of this will be equal like this, and after this it falls like this. So this behavior of this behavior would be average for most of the polycrystalline materials. So most of the polycrystalline materials shows this behavior. So therefore we can explain this behavior on the basis of applied field, direction of the applied field, whether this is in perpendicular direction, whether this is in parallel direction, or any other directions. So it starts from here, here, so it can be averaged like this. So that is why the susceptibility has certain value at temperature will be equal to 0. So thank you. I hope you understand this lecture. Thank you again.